So, you've just been picked up by 3i/Atlas, don't mind the Halloween prop rattling around, because this interstellar visitor has just woken up after perihelion. On October 29th, 2025, it slipped behind the Sun at magnitude 9.5, but its path is already raising eyebrows. JPL's A1 and A2 parameters flag subtle, real, non-gravitational acceleration, and a solar CME slammed its plasma environment days before. Everyone asks, does that mean alien tech or comet physics unleashed? Before we go any further, let's separate the measured facts from the wild theories, starting with what scientists actually see right now. From Earth's vantage point, 3i/Atlas spent perihelion hidden almost directly behind the Sun. This geometry shut down ground-based telescopes for several days, leaving even professional observatories waiting on the sidelines. Yet, the blackout wasn't total. Spacecraft orbiting far from Earth, like the Punch mission, kept their eyes on the prize. By stacking images from late October, Punch managed to tease out a faint signal, 3i/Atlas holding steady at about magnitude 9.5. That's far dimmer than what the naked eye can catch, and just at the edge for mid-sized amateur scopes, even under perfect skies. The trick is that space images don't face the same solar glare as telescopes on the ground. They can look closer to the Sun's limb, picking out objects that would be lost in daylight or atmospheric haze. Still, the raw images are noisy, and the comet's light is smeared by the harsh background. Even with careful processing, the details are limited. No crisp tail, no dramatic jets, just a soft, condensed glow against the solar backdrop. As October gave way to November, the elongation, meaning the apparent angle between the comet and the Sun, began to widen. This subtle shift means the comet is pulling away from the Sun's glare, inching back into the realm of ground-based observation. Astronomers, both professional and amateur, are now watching for the first clear frames as it emerges into the dawn sky. For now, every new image comes with caveats. Brightness estimates are rough, the coma is unresolved, and the tail, if present, is barely hinted at. But the fact remains, despite being hidden by the Sun at its closest approach, 3i/Atlas did not disappear. With each passing day, its optical profile becomes just a bit clearer, and the data trickling in will soon let scientists chase down its exact position and motion. Precise tracking of 3i/Atlas. After perihelion has revealed a subtle, persistent mismatch between its predicted and observed positions, a right ascension offset measured in arcseconds. This isn't a sign of something exotic, it's a well-known quirk of active comets. When astronomers fit orbits to the data, they use a set of standard parameters, A1 and A2, to account for slight, non-gravitational nudges in the comet's motion. These aren't random fudge factors. A1 captures acceleration along the Sun, comet line, while A2 covers sideways drift in the orbital plane. For 3i/Atlas, recent JPL solutions list A1 around 1.7 times 10 to the minus 6, and A2 about 7 times 10 to the minus 7 astronomical units per day squared. To put that in context, these numbers fall right in line with moderately active comets elsewhere in the solar system. The source of these residuals is straightforward: outgassing. As sunlight warms the comet, jets of vaporized ice erupt from its surface, pushing it ever so slightly off course. The effect is small but measurable, especially when precise astrometric data from ALMA and ground-based observatories are stacked up over weeks. The Marsden formalism, the gold standard for comet orbit fitting, uses these A1 and A2 terms to model the extra push. When these parameters are included, the fit between observed and calculated positions drops to within the expected noise, typically inside one standard deviation for plausible values of nucleus size and activity. A JPL scientist summed it up: "We're not seeing a spaceship, we're seeing standard cometary physics, made extreme by a hypercharged solar wind. There's no need to invoke engines or artificial propulsion. The measured accelerations match what you'd expect for a small, active nucleus venting gas as it swings through the inner solar system." While the numbers might look surprising to those outside the field, for comet scientists, they're business as usual. The real intrigue comes from how these natural processes play out under the wild conditions of an interstellar visitor, not from any unexplained anomaly. Plasma isn't just an exotic word from physics class, it's the state of matter that dominates the space around comets like 3I/Atlas. 5 main plasma processes set the stage for everything that happens near a sunlit comet. First is photoionization. Here, ultraviolet light from the sun knocks electrons off gas molecules streaming from the comet, turning neutral atoms into charged ions. Next comes charge exchange. Solar wind ions crash into cometary atoms, swapping electrons and spawning new ions that light up in X-rays. Then there's mass loading. As those fresh ions flood the solar wind, they slow it down and pile it up, stretching and reshaping the magnetic environment around the comet. The fourth process is the bow shock. This is like a wave at the front of a boat, where the solar wind slams into the comet's expanding atmosphere and is forced to slow down abruptly. Finally, there's the ionopause, sometimes called the cometopause. This invisible boundary forms where the comet's own ions push back hard enough to carve out a protective bubble, separating the comet's plasma from the solar wind beyond. Each of these processes is at work around 3I/Atlas right now, shaping its behavior, its brightness, and even the way it drifts through space. Dust grains near 3I/Atlas aren't just passive passengers in the solar wind, they're active players in a microscopic drama. As the comet sweeps through the inner solar system, each grain gets bombarded by high-energy particles and ultraviolet light. This constant exposure builds up electric charge on the surface of the grains. When the charge reaches a tipping point, the grain can't hold together any longer. The result is a tiny explosion. One grain fragments into a cloud of even smaller pieces, each with a much higher area-to-mass ratio. Suddenly, these fragments respond more strongly to solar radiation and electromagnetic forces, veering off or accelerating in unpredictable ways. This process doesn't just shuffle dust around, it can cause sudden spikes in the comet's brightness and brief changes in its apparent motion. Micro-explosions like these are a natural part of comet activity, especially when solar outbursts inject extra energy into the environment. The same mechanism has been caught in action before, most famously by Rosetta at Comet 67P, where a surge in charged dust reshaped the coma almost overnight. For 3I/Atlas, every flash and flicker in the data could trace back to these invisible but powerful dust events. In July 2015, a spacecraft orbiting Comet 67P, Rosetta, caught something no one had quite seen before. As a coronal mass ejection from the sun slammed into the comet, Rosetta's magnetometer registered a surge in the local magnetic field. The readings shot up from a baseline of around 50 nanotesla to nearly 300 nanotesla in a matter of hours. That's not a minor uptick. It's a 6-fold leap, the kind that turns a gentle magnetic breeze into a wall. For the Rosetta team, the surprise was immediate. One engineer, caught on the mission voice loop, called it a magnetic wall. The instrument scrambled to keep up as the plasma environment around 67P transformed almost overnight. This spike wasn't just a curiosity. It revealed that when the sun sends a shockwave through the solar system, a comet's plasma cocoon doesn't respond gradually. It reacts in jumps. The entire magnetic structure can inflate, compress, or even break apart in response to the incoming solar storm. During the 2015 event, Rosetta's particle instruments recorded sudden changes in ion flows and dust activity. The comet's plasma boundary, the so-called cometopause, shifted outward, then snapped back as the storm passed. These changes happened on timescales of minutes to hours, not days. For plasma physicists, the Rosetta 67P event became a textbook case. It showed that comets are not just icy snowballs with a gentle tail, they can be wrapped in magnetic armor, reshaped by the sun's mood swings. The 300 nanotesla spike stands as a concrete number, a reference point for what's possible when a comet and a solar eruption cross paths. ESA's own summary put it simply: CME hits can literally wrap a comet in a plasma blanket, supercharging its environment for hours or days. This is why analogies with Rosetta matter for 3I/Atlas. When a comet rounds the sun during a period of solar fireworks, the plasma and magnetic effects can dwarf anything caused by dust and gas alone. The numbers from Rosetta set the scale for what scientists are now watching for in the data from 3/Atlas, as it emerges from its own solar encounter. On October 21, 2025, the Sun unleashed a massive coronal mass ejection from active region 4246, just as 3I/Atlas neared perihelion. This eruption, captured in white light by the GOES 19C/COR1 coronagraph, blasted away from the Sun's far side, missing Earth but sending a shockwave out across the inner solar system. For objects like 3I/Atlas, timing and geometry are everything. The comet's path placed it near the ecliptic, not far from the longitude of the eruption. When a CME of this scale erupts, its expanding front can sweep through a broad swath of space, especially if it's a wide or so-called halo event. With a launch speed likely exceeding 1,000 kilometers per second, the CME would reach a distance of 1.4 astronomical units, roughly the comet's perihelion, within 2 to 3 days. Propagation models like ENLIL and cone simulations allow researchers to estimate whether such a shockwave might intersect a target like 3I/Atlas. In this case, the available data suggest a plausible window for interaction between October 23 and 26, just as the comet rounded the Sun's far side. No in-situ spacecraft has measured plasma or magnetic fields at the comet's location, so the exact impact remains unconfirmed. However, the physics is well understood from past events. A fast, dense CME slamming into a comet can amplify the local magnetic field by several times, compress the plasma environment, and trigger abrupt changes in the coma and tail. This is not just theory. Rosetta's 2015 encounter at 67P showed a six-fold spike in the magnetic field, with the comet's plasma boundary swelling and snapping back within hours. For 3I/Atlas, the October 21st eruption stands out as the most likely natural trigger for any sudden changes in its plasma environment after perihelion. The absence of a direct hit confirmation means scientists are careful with claims, but the timing and geometry make this CME a prime suspect for any rapid shifts in the comet's activity or trajectory during this critical period. As new models and spacecraft data are released, researchers will be watching for signatures, a kinked tail, a brightness surge, or a drift in orbital path that could tie back to this solar outburst. Until then, the October 20th CME remains a leading candidate in the ongoing forensic modeling of 3I/Atlas's wild ride through the inner solar system. Piecing together the plasma environment around 3I/Atlas after perihelion means working with a patchwork of indirect clues. No spacecraft passed through the comet's immediate neighborhood, so there's no direct measurement of the local magnetic field or charged particle density. Instead, researchers rely on a synthesis of data from multiple vantage points: solar wind models, coronagraphs, and remote sensing images like punch, SOHO, and stereo. Each instrument offers a different slice of the puzzle, but none can capture the full picture alone. The limitations are clear. With only stacked low-signal images and brief windows between solar glare, the tale of 3I/Atlas remains faint and unresolved. Reports suggest a short, almost stunted tail, barely distinguishable from the coma. This could mean the comet is shedding less dust than expected, or that the solar wind has swept the tail away before it could fully develop. The nucleus itself is still just a rough estimate, somewhere in the range of a few hundred meters to perhaps a kilometer across. No sharp silhouette, no clear rotation period, no direct measurement of its shape or spin state. Every parameter comes with wide error bars, shaped as much by what can't be seen as by what can. The forensic models, built by teams at JPL and elsewhere, lean heavily on analogies with better-studied comets like 67P plasma spikes, tail disconnections, and sudden changes in brightness are all plausible under the right conditions, especially after a major solar outburst. But without in-situ confirmation, each interpretation carries a degree of uncertainty. Gas production rates are inferred from faint spectral lines, not directly measured. The active fraction of the surface how much is actually venting remains a guess, bounded by the observed non-gravitational acceleration but not nailed down. These gaps aren't just academic, they shape the boundaries of what can be claimed with confidence. For now, the evidence points to a modestly active, kilometer-scale nucleus with a weak tail, behaving much like comets seen before, if supercharged by a turbulent solar wind. But as the comet moves farther from the sun's glare and into a more favorable sky position, the next round of images and spectra will be essential. Each new observation offers a chance to tighten the constraints, resolve ambiguities, or catch a surprise. The uncertainties are real, but so is the opportunity for discovery as the world's telescopes turn their attention back to this interstellar visitor. November brings a packed calendar for anyone hoping to catch 3I/Atlas in action. On the morning of November 4th, Venus, the Sun, and the comet line up almost perfectly. A rare geometry that might spark some creative speculation online. For observers, though, it means the comet sits just 29 degrees from the Sun, hugging the horizon in the pre-dawn glow. Visibility remains tough, but each day adds a few degrees of separation. By November 5th, a full supermoon lights up the sky, making faint objects even harder to spot, but the elongation edges past 30 degrees. Early risers with a modest telescope and a clear eastern horizon might catch a glimpse, though the comet's magnitude hovers around 10, well below naked eye limits. November 7th marks a turning point. The Sun rotates a cluster of large sunspots into view, raising the odds for more solar flares or even another coronal mass ejection. For skywatchers, the comet now sits 36 degrees from the Sun, climbing higher in the dawn sky. The best amateur window opens between November 14th and 17th, when elongation stretches past 50 degrees and the comet rises well before sunrise. Still, it remains a faint target, compact, with no dramatic tail, and fading as it recedes from the Sun. Most backyard astronomers will need a 4-inch scope under dark skies, and even then, patience is required. December 19th stands out as the closest approach to Earth, about 1.8 astronomical units. The comet will be high in the constellation Leo, perfectly placed for telescopes, but likely even dimmer, around magnitude 12 or fainter. By January 9th, 2020's a multi-planet alignment brings Atlas, Jupiter, Mars, and Venus into the same stretch of sky. This kind of event often attracts bold headlines and viral graphics, but the science stays the same. The comet will be faint, distant, and best studied with careful instruments, not the naked eye. With so many dates and so much online chatter, it's easy to get swept up in hype. A simple rule helps: treat any claim of naked eye visibility, spectacular tails, or alien engines with a red light unless it's backed by peer-reviewed data. For real-time updates, rely on JPL horizons, major observatories, or trusted astronomy clubs. The story of 3I/Atlas is written in careful measurements, not in clickbait. The next few months offer a rare chance to watch an interstellar visitor cross our skies, but the real discoveries will come from patient observation and clear-eyed skepticism. On October 29th, 2025, 3I/Atlas reached perihelion at roughly 1.4 astronomical units from the Sun, with space-based images recording a visual magnitude near 9.5. JPL's published orbit shows measurable non-gravitational acceleration, with A1 and A2 values consistent with active comet behavior, not evidence of artificial propulsion. The Rosetta mission's records from Comet 67P confirmed that sudden magnetic field spikes, such as the 300 nanotesla surge linked to a CME, can sharply alter a comet's plasma environment, a process likely at play after the October 21st CME intersected Atlas. Yet, the true size of Atlas's nucleus and the exact cause of its weak tail remain uncertain due to observational limits and lack of in-situ data. The coming months, especially around December 19th and January 9th, offer rare windows for new observations. As peer-reviewed results emerge, the case of 3I/Atlas stands as a reminder. Understanding interstellar visitors demands both precise data and caution against premature conclusions.